In this example, we're going to integrate the function over the surface of this entire cube, which is cut from the first octant using the planes x equals a, y equals a, and z equals a. Since this cube has 6 different surfaces, essentially we need to perform 6 different integrations. The nice part is that using some symmetry, these 3 planes that lie on the coordinate axes, those are all going to be the same. So we can look at integrating the base, and then we can look at integrating the top, and that would give us these outer 3 sides of the cube. So we're going to do this in 2 pieces, again, with 2 integrations. So the first side I'm going to integrate across is going to be the bottom of this cube. So that is in the xy coordinate plane. That is actually the plane of z equal to 0. So if z is equal to 0, what would my function be? We would have g of x, y, 0, and we would get x plus y plus 0. So we're going to have g of x, y is just x plus y. Since my surface is the plane z equals 0, this is defined implicitly. And so we'll say that our surface f of x, y, z is going to equal z equals 0. And my orthogonal vector, or my normal vector, we're going to let the p-value equal k. So the vector p, which could be I, j, or k, is going to be k, rising up normal to that plane or surface. And this ends up being a pretty simple problem. So we have gradient of f. The gradient of f is just going to equal k. Partial of z with respect to z is 1. So we have 1k. Then the magnitude of gradient f, the magnitude of that, magnitude of 1 is 1. And then the magnitude of gradient f dotted with k, that's the magnitude of 0, 0, 1 dotted with 0, 0, 1. That's just going to be 1, the magnitude of 1, which is 1. So by definition here, my integral, the double integral of the surface of g, and then my surface area differential, that's the same as the double integral of r. G in this case is just x plus y. And my d sigma, that is going to be just the magnitude of gradient f divided by the magnitude of gradient f dotted with k, so 1 over 1. And then dA, or dx dy. So we just have 1 dx dy. And my region R, that's just this cube. So my x goes from 0 to a, and my y goes from 0 to a. So this is the double integral from 0 to a, 0 to a, x plus y, dx dy. All right, so first we're going to integrate with respect to x. So I've got 0 to a. X with respect to x becomes x squared over 2. Y with respect to x comes yx. And we have x equals a, x equals 0. We will still need to integrate with respect to y. So I'll plug in a for x in both of these situations. That gives me the integral from 0 to a. I have a squared over 2 plus ay dy. Of course, when I plug in 0, that would zero out both of those terms, so there's nothing to subtract. So integrating this again, now with respect to y, I have a squared over 2y plus a y squared over 2. And we need to evaluate y equals a, y equals 0. which gives me a cubed over 2 plus a cubed over 2, which is just a cubed. So the surface integral over the base surface is a cubed, right? So this surface integral is a cubed. And by symmetry, if we calculate it along the xz plane as well as the yz plane, we're also going to get a cubed, right? So we now know this back surface and this back surface over there. So essentially, we have a cubed plus a cubed plus a cubed plus that surface integral for 3 other sides. So as we just stated, we just found the surface integral along or across the base. So now we're going to look at this surface integral for the top, and that's going to give us the same as these 2 outer sides. And along the top, that is the plane z equals a. So the base was the plane z equals 0. Now we have the plane z equals a. So what does that do to our function? We have g of x, y, z. Originally that was equal to x plus y plus z. But now we're going to have g of x, y, a. So that's x plus y plus a. And then my surface can be implicitly defined as f of x, y, z equals a. And of course, my normal vector to this, my p vector in this definition is going to equal k. So first things first, gradient of f is just going to equal k. Then the magnitude of gradient f is equal to 1. And the magnitude of gradient f dotted with my k vector, that will also equal 1. My d sigma is equal to the magnitude of gradient f divided by the magnitude of gradient f dotted with k. So that is 1 over 1, and then we've got dA, or rather dx dy. So in this case, my integral setup is very, very similar. It's just that my g function is a little bit different. So that double integral of s of g d sigma is the double integral over r. My function is x plus y plus a. So I've got x plus y plus a, and then I have the 1 dx dy. That's my d sigma value. So I don't really need that 1 there. My bounds, of course, we come up and look at our picture. My x value is going to go from 0 to this line A. Same with my y value from 0 over here to A. So my final setup before I integrate is going to be 0 to A, 0 to A, x plus y plus a, dx dy. And I feel like that is pretty redundant for me to work through with you. We just have this one extra term here. So I'm going to work that out real quick. Integrating with respect to x, we end up with 3a squared over 2 plus ay. And then we'll do this integration now with respect to y. And evaluating that integral, we end up with 2a cubed. So 2a cubed is the surface integral for this top plane. And that would also be the surface integral for this outer front plane and this plane over here on the right, all by symmetry. So our first three sides were a cubed, right? We had a cubed plus a cubed plus a cubed. And then we've got plus 2a cubed plus 2a cubed plus 2a cubed. And all in all, that gives us 9a cubed. So that represents the surface integral, calculating the integral of this function across that entire cubic surface. As always, if you have any questions, feel free to email me. May the force be with you.